All right, so we have done sine functions, cosine functions, and now we're going to turn our attention to the tangent functions. So tangent functions are going to look a little bit different than the sine and cosine, where sine and cosine ones look like little roller coasters. Tangent does not follow that same pattern. So take a unit circle and form an angle in standard position. Point P is the intersection of the terminal ray and the circle. The tangent function gives the slope of the terminal ray. So if I had my graph, let's just say went ahead and did this. Here's my P. Okay. And then I draw, there's Y values, there's my X, here's theta. My tangent, remember that my tangent of the functions are always opposite over adjacent. That's what my SOHCAHTOA tells me. So y over x, which is the slope, right? The slope is y2 minus y1 over x2 minus x1. So it is the slope of the terminal ray. So the slope of the terminal ray can be described by the ratio of the change in y values to the change in x values between any points on the ray. So again, that's the y2 minus y1 over x2 minus x1. The tangent function is also the ratio of the sine function to the cosine function. So exactly what we just said, it's sine of theta over the cosine of theta, right? As long as cosine of theta does not equal 0. So remember, cosine of theta is going to be in the denominator, so you cannot be having that 0 down in the denominator. So, for example, it has a measure of pi over 3. What is the slope? Well, if we remember on our unit circle, pi over 3 has the points of 1/2, comma, square root of 3 over 2. So my tangent would be equal to square root of 3 over 2 divided by 1/2. So remember, that's a fraction divided by a fraction. Means I do square root of 3 over 2 times 2 over 1. My 2's are going to cancel out, leaving me with just the square root of 3. Okay. I don't think I need to go over all of this because it's the same thing. So it's just divide the 2 and simplify, and you'll get the tangent. The tangent you can just get on your own. Now, the only one I will do is number 4. You should practice these on your own, but number 4 is the only one I will do with you right now. At 3 pi over 2, my points are 0, comma, -1, which means that my sine is -1 over 0. So again, I cannot have this. So my my point here is undefined. I actually don't have a tangent for 3 pi over 2, and that will come into play when you actually see what the function of tangent looks like on a graph, okay? So now we're going to kind of go through a bunch of these little uh, points. So think about the slope values of the terminal ray as it moves around the unit circle. So the slope starts as 0, right? I mean, I'm starting down here, right? That would be 0 over 1, which is equal to 0. It gets larger until it approaches infinity. And at pi over 2, my slope is undefined. Because again, it would be 1 over 0. Then the slope is very negative, but starts to grow towards 0. So I'm basically going like this. Then I hit here and I'm undefined. Then I go down all the way to pi. And it's once we reach an angle of pi, as I just said, we are back to a slope of 0 again. As soon as we pass it, the slope will be the same as it was in quadrant 1. It's going to start moving up. Every 1/2 revolution of the circle, the tangent function repeats. So I basically go from quadrant 1, I hit that 90 degree, that pi over 2, and then I start over, I go down. Then I hit another pi, I hit pi, I'm going back up, hit another pi over 2, stop, and then it keeps going. So meaning the period of tangent is pi. I know that this probably makes no sense, but remember that when we do these on the graph, um, they your x values are in terms of pi. Your x values are no longer just whole numbers. So here we have each time the cosine of theta is equal to 0, tangent of theta is undefined. What angle on the unit circle does this occur? So it occurs at pi over 2. It occurs at 3 pi over 2. And then I just keep going. I keep on adding that pi over 2. 5 pi over 2. And I'm going to stop, I think, at 5 pi over 2. But now that means that on my graph, for the graph, this is represented by vertical asymptotes. So at pi over 2, there's a vertical asymptote. Three pi over 2 is another one. Here's another one at negative pi over 2, at negative 3 pi over 2, and so on and so forth. So now for the graph of f of theta equals tangent of theta, a vertical asymptote appears at every theta equals pi over 2 plus k pi for integer values of k. So when we see all these variables, I feel like we just get really confused, but we're going to actually see it put into practice, and I think that that will help clarify what all of these letters mean. For the graph of tangent b of theta, the period is pi over b. A vertical asymptote appears at every theta equals pi over 2b plus k pi over b for every integer values of k. So now what does that mean? Well, let's see our example here. We have tangent of 2 theta. So that means that my period is going to be equal to pi over 2. Remember that this is my b, right? So my period is pi over 2, meaning that at every theta, it's pi over 2 times 2 plus k pi over 2, which is going to be the same thing as saying pi over 4 plus k pi over 2 for integer values of k. Okay, so that's what that basically means. It's not anything, I don't think it's too complicated, but you can try 6 on your own, and I will give you the answers again during class time. So here we have characteristics of the tangent graph. So as you can see, the tangent graph is like a mini graph uh, between a bunch of vertical asymptotes, right? So the tangent function increases. Its graph changes from concave down to concave up between each set of asymptotes, right? So I'm here, down, up, down, up, down, up. The point where it changes concavity is called an inflection point. So they're always having an inflection point pretty much at that 0 marker. So let's go ahead and fill out and see these little bullet points. So the graph of g of theta is equal to a tan b theta plus c plus d. So this is the same transformation that we've gone through, only now it's in regards to the tangent function. The constant a creates a vertical, actually I'm going to change this to the black marker, creates a vertical dilation by a factor of absolute value of a. If a is less than 0, there is a reflection over the x-axis. Okay? which makes sense because it is a negative. So a negative is a reflection. The constant b creates a horizontal dilation and changes the period by a factor of absolute value of 1 over b. If b is less than 0, there is a reflection over the y-axis. So these are all rules of normal functions, right? The constant c creates a horizontal translation, a phase shift by negative c units, and the constant d creates a vertical translation by d units. So basically, that c constant creates a horizontal translation by negative c units. That's essentially the same thing that we've been doing. That makes it so that when I say plus 4, it's really a shift to the left. It's just creating that opposite uh, translation, okay? And then you have these two examples that you are to do on your own, and then I will give you the results when you have them finished. And then that is the end of 3.8.